Alright, now let's talk about the formation of the Earth. So in this video we're going to describe the environment of the early solar system, and we're going to define key concepts related to the composition of our planet and the availability of water, such as frost line and condensation temperatures. And then we'll contrast the elemental composition between our Earth and the solar system at large. So when we talk about the formation of our solar system, this is the raw material that we have. We have a lot of hydrogen and a lot of helium. That's over 95% of the starting material. There's a few percent of a couple other elements like carbon, oxygen, and a much smaller amount of these rock-forming elements like silicon and iron. So this plot is showing all the elements normalized to the availability of silicon at 10 to the 6 or 1 million units of abundance here. There's a lot of rare isotopes from recent supernovas. So to go through the timeline that we think the solar system formed, this starts off with a solar nebula, a big collection of gas that's produced from past supernova events and other dying stars. So this is going to be providing the heavier elements needed to sort of form hard planets. So this begins with the material from this solar nebula being drawn into the center. This is sort of the process forming our proto-sun. Here is most of the mass of this nebula ends up being drawn into the center to form the proto-sun. Things in that proto-sun get progressively denser, they get progressively hotter. In the meanwhile, there's some dust that remains sort of floating around in this protoplanetary disk. That dust starts off microscopic, but it starts sticking to dust that's around and forms these bodies called planetesimals. You can think of these as asteroids flying around into space. Now at some point, the protosun gathers enough material where the center is so dense that fusion of hydrogen into helium can start happening. And that's going to be the major energy source for our solar system up until this very day. And in the meantime, these planetesimals will start to collide into each other, and this will sort of start to grow the planets or accrete them. This is mainly due to gravity sort of pulling in the debris from these collisions and forming a round surface. So if you want to look at this, this is a nice schematic of this process here. Basically all the planetesimals, because they're constantly growing, they're changing in mass and their orbits are slowly shifting. So that puts them on the collision courses to hit other planetesimals which grow and grow. And eventually this very kind of busy protoplanetary disk gets into a much less crowded field of larger planetesimals, and then eventually a small number of planets that we observe today. And so these are the planets of our solar system. You know them: Mercury, Venus, Earth, Mars. These are the rocky planets, followed by the gas giants Jupiter, Saturn, Uranus, and Neptune. So now let's think about why the outer planets are so much larger than the inner planets, and also why the inner planets are rocky and the outer planets are not. In order to really think about this, we need to think about the temperature of the early solar system. And it's common here to use units that may be a bit unfamiliar to you. This is the Kelvin temperature scale. To convert from Kelvin to Celsius is very easy. You just add 273. And the reason for this is that 0 Kelvin here is signifying absolute zero. This is the point where there's absolutely no molecular motion. Things are so cold that not even the molecules themselves are moving around. So this is a nice sort of lower bound for how cold things can be. So anyway, Earth today is around 280, 290 Kelvin at its Earth's surface. That's slightly above the freezing point of water, which is why we have liquid oceans today, although we do have some ice caps. But early Earth, all indications suggest that it was a lot hotter than currently. So early Earth is probably closer to 500 degrees Kelvin, and the planets close to the sun were even hotter, and then planets further away were even colder, sort of below the freezing temperature of water. So these temperature gradients in the early solar system have a huge importance in terms of what the planets end up looking like. And this is because only things like solids and liquids can actually condense when planetesimals are forming. Elements that stay in gas phases will just keep flying off into space and not collect as part of this growing planet. So every single element has a point at which it will condense. This is called a condensation temperature. So when a temperature exceeds a condensation temperature, the element will be found in the gas phase. When it's less than the condensation temperature, it'll be found in a solid phase. So you can see here we can start with water as ice, marked down here, When temperatures are above this point, then water will mostly be in a gas phase. It won't be part of the growing planet. If it's colder than this, then water will join the growing planet. So it's common to expand this to other elements. So things like water are called volatile elements, or volatile molecules. These are things that sometimes on Earth are associated with rocks, but under moderately high temperatures, these can turn into gases and become separated from rocks. On the other hand, you have elements like magnesium, iron, and silicon. It's called this main component group. Sometimes this is called the refractory group. These are things that stay solid even at really high temperatures. So these are the first elements to condense when the solar system was made, and they're forming the rocky planets. So we can go back to our temperature gradients at the start of the solar system and see how this plays out. This red dotted line here is basically the condensation temperature for iron and for silicon. Iron condenses as iron metal, but silicon has to react with oxygen to form a solid silicon dioxide. This is actually a good way for planets to pull in lots of oxygen, even though things like water don't condense or oxygen gas don't condense. So closer to the sun here, even silicon and iron are part of the gas phase, so they won't form any planets even closer to the sun. But for everything further away, the temperatures are right for the planetesimals to be iron-rich and silicon-rich. And that includes Earth. Now, about halfway between Mars and Jupiter, that's where the water condensation line is. That's where water can turn into a liquid phase and start joining these growing planetesimals. So that applies for things like Jupiter, Saturn, Uranus, Neptune, and Pluto, and even these latter ones. These planets can basically benefit from other condensed volatiles that we think of as gases today, things like methane, ammonia. These conditions in this part of the solar system are cold enough that these condense and start joining the growing planet. And so this is important because this sort of controls where the water in the solar system ends up. It can be a misconception that because Earth is the only planet with oceans, that water is rare in the solar system. That's not true. There's lots of water in the solar system. It's just not in these rocky planetesimals because the conditions at the start of the solar system were too hot. So this concept is often illustrated in what's called a frost line. This is the water condensation point. So when you're further away from the sun, you can have accreting planetesimals that grow as rock and ice. But on the other side of the frost line, on our side of the frost line, things accrete just as rocky planetesimals. And this extra boost from the combination of rock and ice for the gas giants like Jupiter and Saturn is one of the reasons why they're able to grow so large. Essentially, this rock and ice combined can exert enough gravitational pull that these protoplanets can start pulling in things like hydrogen and other gases. And that's what makes them grow so big. Jupiter is mostly gas. It's a gas giant. But the only way it can retain that hydrogen is if it has this dense core in the center from rock and ice. So as our solar system forms, most of the mass is pulled into the sun. The rest of the mass goes to make the planets, especially things like Jupiter and Saturn. But there is some extra material, especially water, that escapes this. These are found in these icy comets in the Kuiper Belt beyond Pluto, and also in the Oort cloud, which is these very sort of long period comets that only rarely sort of come into our solar system on their irregular orbits. But there's really vast reservoir of water that's outside of the frost line that visits us every now and then as these comets sort of come closer to the sun. So to sum up, the combination of the solar system temperature gradients and these unique points where different elements turn from a gas phase into a solid phase really define the chemical reactions in the formation of our planet Earth. And you can see this by just comparing what our Earth is made of compared to what our solar system and what the universe is made of. The universe is mostly hydrogen and helium. These are mostly gases that won't condense under anything but the absolute lowest temperatures. In contrast, our Earth is 1/3 iron, 1/3 oxygen, and a good part silicon and magnesium. Iron, silicon, and magnesium are refractory elements. They condense at high temperatures, and when silicon and magnesium especially condense, they pull oxygen with it. So that's why our planet has so much oxygen involved. This is not oxygen gas. This is oxygen bound in minerals. So these elements, iron, silicon, magnesium, oxygen, these are all elements that are formed inside stars. So it's not just that these elements are refractory, they're also abundant enough to form the main blocks of these planetesimals and of our Earth. So it's really the combination of abundance and condensation temperatures that explains what our Earth is made of today. So in this video, we described the early environment of our solar system. We talked about how things like condensation temperatures influence which elements made it onto planet Earth, and also this frost line concept to explain why Earth is relatively rare in water compared to some of the other planets. And also considering how much water is at the edge of our solar system where temperatures are even lower. This leads to a unique elemental composition of Earth compared to the solar system. It's very rich in silicon, magnesium, and iron, and oxygen compared to the starting materials, which are mostly hydrogen and helium.